Okay, hi. Thanks again. My name is Matthew Brister, and I'll be talking about ancestral nuclear bases. So I'm going to completely change subjects and talk about physical chemistry. So my group is interested in photochemistry. So it's the monitoring of photochemical and photophysical events. So when you think of a photophysical event, it's the conservation of energy. A photochemical event is the breaking of chemical bonds. So to help illustrate that, I'm going to have just the Jablonski diagram. So we have our ground state energy, a singlet manifold, and a triplet manifold. When we talk about manifolds, we're talking about multiple excited states. So what we're interested in is what happens after photoexcitation. So we have photoexcitation, we populate the singlet manifold. From there, we can have internal conversion down to the lowest energy singlet state. Once there, the population can either emit a photon through fluorescence, non-radiatively decay back to the ground state, or intersystem cross to the triplet manifold. Again, once in the triplet manifold, we can see internal conversion to the lowest energy triplet state. And then we can see emission of a photon, phosphorescence, or non-radiatively decay. So it's important to note that these are all photophysical events. Okay? But we also are interested in photochemical events. Photochemical events can occur from either the singlet manifold or the triplet manifold. The longer a population stays excited, obviously the higher the probability for photochemistry to occur. Also, the majority of organic compounds, when exposed to UV light, do photochemistry. Either they break down and form photoproducts, or they just degrade. So in order to monitor photophysical and photochemical events, we use what's called transient absorption spectroscopy. So when we think of it, think of a UV vis. The UV vis monitors ground state to electronic state transitions. What we're monitoring are electronic transitions to higher excited state transitions. So in order to do that, we use a pump probe technique. So we have a pump pulse, excite a portion of the population, and a probe pulse is going to monitor the transition from one excited state to the other. So our experiment begins when the pump and probe both are aligned in space and time. So what we can do is we can monitor this transition here, and we can get some spectral information, just like with the UV vis. But in this case, we're monitoring, let's say, this transition. We can also delay our probe pulse in time to get temporal information. So we can monitor the population decaying over time and obtain lifetime. So we can get both spatial and temporal information from our spectral data. So what are the fundamental questions we're trying to answer? One are, what are the molecular origins of life, and why did nature select the nuclear bases of DNA and RNA? So first off, the current form of RNA is thought to come through a complex chemical and biological evolution event. To understand the molecular origins of life, we need to identify promising ancestral RNA candidates. So we can no longer find ancestral RNA like sequestered somewhere on Earth. So essentially, we have to actually just rediscover it or find plausible candidates. To that effort, Cafferty and Hudd took essentially a bunch of molecules, in this case 81, and pulled them from the prebiotic soup and applied selection criteria to them. One of them was the ability to hydrogen bond with the canonical nuclear bases, so that eliminated up to half. The other would be able to show a synthetic pathway for sugar attachment to these ancestral candidates. And finally, being able to self-assemble in water. So that left with barbituric acid, we're going to abbreviate BA, and 2,4,6-triaminopyrimidine, abbreviated TAP. So when we look at barbituric acid and TAP against the canonical nuclear bases of uracil, thiamine, guanosine, cytosine, guanosine, adenine, we can see some similarities between BA and uracil. We see a substitution of the carboxylic at the 6th position, where for TAP we see a substitution at the 6th position and at the 2 position here with an amine group. Okay. So one of the interesting phenomenons of the nuclear bases is the ability to be what's called photostable. The idea is we can excite the nuclear bases, they can take this high electronic energy, internally convert them at an ultra-fast time scale back to the ground state, and essentially stay relatively stable and not photodegrade or do photochemistry. So one of the important criteria that we postulate that was overlooked in the study was obviously the ability to be photostable. So you can see here with and without the ozone layer against the normalized absorption of RNA and DNA, we see that even though there's a small cross-section here, we all know that if you stay out in the sun long enough, you're going to get a sunburn and then eventually form skin cancer. So even though you can, there's a small cross-section here and the ozone is filtering out a lot of the UV radiation, we can still mutate our DNA. So this is even more important, the idea of photo stability, when you think of the prebiotic Earth, because they wouldn't have the protection of the ozone layer at the time. So as I said before, the nuclear bases, the canonical nuclear bases, have been shown to have ultra-fast internal conversion lifetimes of about less than a picosecond. Okay? So why is this ultra-fast? So first off, when I was talking about the Jablonski diagram, it's a super simplification. You have to think of it as a potential energy surfaces. So when you excite from one potential energy surface to another, you essentially say, according to the Jablonski diagram, you're going to follow the potential energy hill down to a minimum, then internally convert. What ends up happening for the canonical nuclear bases is there is what's called a conical intersection, a point where we can bypass this minimum and go directly to, in this case, to the ground state upon photoexcitation. In this case, it gets to the what's called a hot ground state. So it's essentially the ground state, electronic state, with extra vibrational energy. Okay, and that eventually dissipates as heat. So what we've learned so far, we got the longer molecules stay excited, the higher the probability for photochemistry to occur. We have nuclear bases exhibit ultra-fast lifetimes, contain conical intersections, and photo stability is a definite key requirement for any ancestral candidate. So to that effort, we took barbiturate acid and BA, and I do assure you the data does look better. It's just the conversion between Mac and PC. But so we excited at 270 in this case, so you can see here for TAP and BA in a PBS buffer solution. So when we did our transient absorption, when we first did it for BA, we are essentially populating what's called a pi-pi singlet state upon photoexcitation around 500 nanometers. From there, we can see this band decrease at 500, this band increase at 350. And we've assigned that to the internal conversion from the pi-pi singlet state down to a hot vibronic ground state. From there, we can see that vibronic ground state, this long absorption tail, start to decay to essentially have no change in absorption. For TAP, we have absorption at around 600 upon photoexcitation. We see the 600 nanometer band start to decrease, a 300 nanometer band increase during very short timescales. And so you can see here, in this case, we assigned it from a pi-pi transition to an n-pi transition in the singlet manifold. And from there, it would just non-radiatively decay back to the ground state. So both of these processes happened for BA on a sub-picosecond time scale. And this, for TAP, it took about, I think, 3 picoseconds. So in summary, we can see here we have the kinetic traces of both BA and TAP. We can see here with our time scale that's happening again on an ultra-fast lifetime. And here we can see it takes about roughly 20 picoseconds, but the lifetime of that event is actually like 5. As I said before, BA and TAP look very similar to uracil and cytosine. Since no high-level computational results have been done for BA and TAP, we can theorize what is possible from the library of conical information from the uracil, in this case, and cytosine, that have been done. So they have shown conical intersections for uracil to be at this 5,6 carbon. So it's essentially an ethylenic twist. So when you photoexcite your uracil, in this case, you get this ethylenic twist, which twists that torsional angle and forces the conical intersection. So we hypothesized, since for BA, we actually don't have a double bond, making that twist even more likely. So it would exhibit even a faster lifetime than uracil does. And for cytosine, it actually has a couple of conical intersections, one out of an outer plane puckering of the amino group at the 4 position, and an outer plane puckering at the 6 position. So if they're similar analogs, we can theorize that, again, for TAP, it could possibly do a C4 out-of-plane puckering to access that conical intersection, much like cytosine does. And I'd like to thank everyone for listening, the National Science Foundation, Dr. Carlos Crespo, my advisor, and my current group members. And I'll be happy to take any questions.
Questions for Matthew?
Just out of curiosity, has anybody actually tried synthesizing DNA with these new nucleobases in them? And
Not to my knowledge.
Okay.
So yeah, people are looking into the cytosines. I know for they've been able to show like prebiotic synthesis. So the idea is being able to attach the sugar group. But I don't know if anyone's actually gone beyond like doing the oligomers and like trying to make hydrogen bonding occur like that.
Okay, that'd be cool.
Yeah.
All right, one comment on that last comment before I ask you a question. We have done, so this work is based upon work in my group, the HUD group at Georgia Tech. We have done some substitutions into DNA and have shown that it still does base pair from there. I mean, it reduces it, but it still can effectively do it. So it doesn't completely destroy it. All right, now for you. Have you considered attaching sugars to it and checking for their photostability?
Yeah, so we're a physical chemist group, so we actually don't do much synthesis at all. We actually purchased our molecules from Sigma. So if somebody has them, if you guys make them, we'll take a look at them.
Okay, yeah, we can talk about it. It's shockingly easy to attach ribose to it.
Yeah, right. It is a very simple synthesis, but we, like I said, we don't do it. Most of our lab space is all instrumental. It's just all laser tables, and we have a small little cramped workspace for wet work.
Is that an experiment you'd be interested in?
Sure, yeah.
All right,
we'll
talk
do that.
about it later.
Yeah.
Okay, any further questions? Okay, let's thank Matt one more time.